Hello and welcome, guys. Today we're going to be going over general probability rules. By the end of today's lesson, you should be able to apply some of the rules that we've learned in probability, both the addition as well as the multiplication rules. Please don't forget to watch all the videos and do all the homework on Sapling Plus. So here are the formal rules of probability. We have the addition rule, which is the probability of A or B is the probability of A plus the probability of B, as long as they're disjoint. We also have the probability of A or B, where we have to subtract the intersection. That's called the general addition rule. We have the multiplication rule, where the probability of A and B is the probability of A times the probability of B, but that only works if they're independent. And then we have our general probability rule, which works anytime, which is the probability of A and B is equal to the probability of A times the probability of B given A. So let's go ahead and apply this with a couple of examples. I strongly suggest that you pause each video after I present each question and try to answer it on your own before you look at the solution. And then once you think you have a satisfactory answer, go ahead and unpause the video and then see what the actual solutions are. So suppose you want to randomly select 3 cards from a standard 52 card deck, and we want to find what's the probability of getting 3 hearts. So go ahead and see if you can answer this question, and then once you have an answer, go ahead and see what my solution is. So this question asks, what's the probability of 3 hearts? What this question is really asking is, what's the probability that the first card that we choose is going to be hearts, and that the second card we choose is going to be hearts, and that the third card that we choose is going to be hearts. And we're talking about pulling cards without replacement. And what that means is I'm going to drawn a card, I'm not going to put it back into the deck, I'm going to draw another card, I'm not going to put that back into the deck, and then I'm going to be drawing another card. In order to answer this question, we have to use some conditional probabilities. So this is going to be, what's the probability that the first card is going to be hearts? Because this is an AND problem, we know we're going to multiply. And so we have to multiply it times the condition that we're going to get hearts the second time, given that the first card was already a heart. For the third card, I have to say, what's the probability I'm going to get a heart, given that the first card was a heart, and the second card was a heart. So this is what we have to calculate. So if you think about a standard 52 card deck, there's going to be 13 hearts in the deck out of 52. So what we're going to have here is the probability of getting 1 heart randomly out of the 52 cards is going to be 13 out of 52, times the probability that we're going to get another heart, given that 1 heart is already taken out, right? So 1 card is already taken out. The probability that we're going to get another card is now 12, because 1 of the hearts has been taken out. But not only does it affect how many hearts are in the deck, but it also affects how many total cards we have. So now, because we pulled out 1 heart, we now only have 51 cards. Times the probability we're going to pull out another heart. Well, now there's 2 hearts less in the deck, so now there's only 11 hearts, and now there's only going to be 50 cards in the deck. So if we multiply that, we're going to get 1,716 over 132,600. And this is going to reduce to 11 over 850, or if we turn it into a proportion, it'll be approximately 0.0129, or if we turn it into a percentage, 1.29%. So there's a 1.29% chance that if I draw 3 cards from a standard deck, that I'm going to get 3 hearts in a row. Okay, so let's go ahead and try another problem here. What's the probability of getting 3 cards lower than 9, counting aces as 1? Go ahead and pause the video here and see if you can answer this question. Okay, so in order to answer this question, what this is asking us is, what's the probability that we're going to get 3 cards less than 9? So including aces as 1, we have aces, 2s, 3s, 4s, 5s, 6s, 7s, and 8s of hearts, clubs, diamonds, and spades. So that's going to be a total of 32 cards out of the 52 are going to be cards less than 9. So what this is really asking us is, what's the probability that our first card is going to be less than 9, times what's the probability that the second card will be less than 9, given that the first was less than 9, times what's the probability that the third card will be less than 9, given that the first and second cards were less than 9. So in order to do that, we have to count how many cards were less than 9. So once again, there's 32 cards that are less than 9 because ace, 2, 3, 4, 5, 6, 7, 8, and there's 4 suits all over 52. Once we get one of those cards, the probability that we're going to get another one is going to be 31 because we have one less because we got drawn one, all over 51, times the probability that the third card is less than 9 is going to be 30 over 50. And so if we multiply that together, we're going to get 29,760 over 123,600. And of course, we can reduce that. And we get 248 over 1,105. And if we turn that into a decimal, we're going to get approximately 0.224 or 22.4%. So let's go ahead and try another one here. And this one is going to mix these two questions together. So what would be the probability of getting 3 hearts or 3 cards lower than 9, counting aces as 1? See if you can answer this question on your own, and then come back to see what the solution is. Okay, so what this question is really asking is what's the probability, so once again, what's the probability that we're going to get 3 hearts or 3 cards less than 9? If we use the addition rule, it tells us that the probability of 3 hearts or 3 hearts less than 9 is equal to the probability of 3 hearts, which we've already calculated, plus, because it's an OR problem, the probability of 3 cards less than 9. But don't forget, we have to always subtract anything that we've already counted twice. So any kind of intersection. Are there any cards that are both hearts that are less than 9? And the answer is yes. So we have to subtract the probability of getting 3 hearts less than 9. So earlier we said that the probability of 3 hearts was 13 out of 52 times 12 out of 51 times 11 out of 50. We also said the probability of 3 cards less than 9 is going to be 32 out of 52 times 31 out of 51 times 30 out of 50. Now the only thing we have to do now is calculate what's the probability of 3 hearts less than 9. Well, the probability that the first card is going to be less than 9 is going to be 8, because there's 8 hearts that are less than 9, including aces as 1s. So it's 8 out of 52, because there's 52 cards in the deck, times the probability that we're going to get 2 hearts less than 9, which is going to be 7 out of 51. So the probability that the second card will be a heart that's less than 9 is going to be 7 out of 51. And the probability that the third card will be also a heart that's less than 9 is going to be 6 out of 50. And so if we calculate this, we're going to get here, we said that this was 0.0129 plus, and we said that this was 0.224, I'll go 4 decimal places, minus, and if I calculate this, I get 0.0025 approximately. And so let me go ahead and say that this is approximately. So if we go ahead and calculate this, this is going to add up to 0.2348. Okay, so if you got 0.2348 for this problem, good job. Let's go ahead and move along here. When it comes to conditional probabilities, we do have a rule that the probability of A given B is equal to the probability of A and B all over the probability of B. Now, rather than trying to memorize this formula, it's better to understand what this is saying. So the probability of A and B is equal to the intersection, so that's going to be in the numerator because it's both A and B. We know that B has already occurred, so we're trying to figure out what's the probability of A now that B has already occurred, so that means A and B have both occurred. And remember, whatever we're given, that becomes our new denominator. So the probability of B becomes our denominator. The probability of B cannot be 0 because it doesn't make sense for us to divide by 0. And because of the fact that B has already occurred, there's no way that the probability of B can be 0. We could also turn it around. We could say that the probability of B given A is equal to the probability of A and B divided by the probability of A. So just depending on what you're given. If you're given A or if you're given B, you're going to use the respective probability rule. Okay, it's important to note that when we examine conditional probabilities, the total number of probabilities becomes limited. In other words, as we're given information, our population or our number of possibilities always diminishes. It always gets smaller. For example, let's look at a school where there's 500 students. 150 of them are in band, 280 of them are athletes, and 50 participate in both. We want to find the probability of randomly selecting a student that's an athlete given that they're not in band. So if we want to answer this question, let me go ahead and pull over my whiteboard. So let's go ahead and answer this using Venn diagrams. I'm going to let A represent athletes and B will represent band members. Remember, whenever we deal with Venn diagrams, we always want to start with the intersection or the middle piece. And so we want to start with how many people are both athletes and band members. And so we see that there are 50 people who participate in both. So there's 50 students who are both athletes and band members. Now, if we go to just the athletes, it says that there's 280 athletes. And so what we want to do here is we want to figure out how many athletes have we not counted so far. So we've already counted 50 of the athletes. And so we know that there's going to be 230 more athletes that we have not counted. We also have counted 50 band members, and so we want to figure out how many more band members there are that we have not already counted. And so there's going to be 100 more band members. So if I add 100 plus 50, that's going to give us our 150 band members. And if I add 230 and 50 together, that's going to give us our 280 athletes. And if we add all of these together, we're going to get 380 students so far. So then that means that there's 120 students that are unaccounted for. So there's 120 students that are not in band and they're not athletes. Okay, so that being said, we want to now figure out what's the probability if we randomly choose someone that the person is going to be an athlete given that they're not in band. So our new population of people are those people who are not in band. Anyone who is in band is no longer part of our study, is no longer part of our little probability problem here. So anyone who's in band, I'm going to go ahead and cross them out. So these people in band, anyone who's in this circle of band right here, they're no longer part of what we're looking at. And so if I take our new population, which in this case happens to be 230 plus 120, which is 350, and we want to figure out what's the probability that we're going to get an athlete from these people who are not in band. And so who are the people who are both athletes and not in band? So that's going to go in the numerator, and that happens to be these 230 people. And so in this case, the probability that we're going to randomly choose someone who's an athlete and not in band is 23 over 35 if we reduce that. And if we get a decimal, we're going to get 0.657, or approximately 65.7%. Okay, let's go ahead and look at another example. Let's look at data from the Titanic. I have a table here that's incomplete and it has some missing information. Let's go ahead and see if we could complete this table given the information that we have. So we know that there were 367 males who survived out of a total of 711 people who survived. Also amongst the males, there were 1,731 total males on board the Titanic. There were also 2,201 people who were on board the Titanic, and that includes all the passengers as well as the crew. If we do a simple subtraction, we could see that from the males, there were 1,731 males and 1,364 of them died. We could also see that if there were 711 total survivors, there were 344 female survivors. I could also calculate that since there was 1,731 males, there must have been 470 females. We could also then say that there were 126 females who died, which is a total of 1,490 people who died aboard the Titanic. So go ahead and see if you could calculate the probability of these events. Pause the video now and then check your work afterwards. So the probability of picking a person who survived at random from the list of people who were on the Titanic were 711 out of 2201. So if you got 711 out of 2201 or 0.323, that is correct. The probability of picking a male in this group, so we want to find the total number of males, is 1,731 over 2201. Again, so the total number of people on the ship is 2,201. So the probability of that is approximately 0.786. The probability that someone's both female and survived, which that's going to be represented here by 344 women, is going to be 344 over 2,201. Now we get to the conditional probabilities. When we get to the conditional probabilities, that means that our totals are going to change based on the given information. So here, the first one, number 4, says, what's the probability that someone survived given that they're female? So we're only looking at the group of females. So the total number of females is 470. Of those 470, the probability that they survived was 344. So we're going to say that this probability is 344 over 470, or approximately 0.732. The probability that someone's male, given that they survived, we're only going to look at the survivors, which is 711, and the probability that they're male, given that they're survived, is 367 over 711. The probability that someone died, given that they're female, once again, we're only looking at the female group, and the probability that they died was 126 out of the 470. The probability that someone is male, given that they died, well, that's going to be this group right here. We're only looking at those who died, which there were a striking 1,490 people who died on board the Titanic, and of them, 1,364 were male. So the probability that someone was male, given that they died, was 1,364 over 1,490, or approximately 0.915. The probability that someone's female, given that they survived, so we're only looking at survivors, and the probability that they're female is 344 out of 711, approximately 0.483. So given this information, answer this question. Was being male independent of survival? And can you justify your solution? Pause the video now and see if you can answer this question. So the probability of being male is not independent of survival, because the probability of male is not equal to the probability of being male given that they survived. So we see that those are two different values. If those values are not the same, then that means that they are not independent events. And that means that gender did have something to do with whether or not they survived. There was an association between gender and survival. Okay, so let's look at a couple more examples of using conditional probabilities, but now what we're going to do is we're going to look at some tree diagrams. See if you can answer the following. Suppose at a certain company, 5% of employees use drugs. The company decides to test all of its employees for drugs with a test that's 99% successful. It correctly identifies 99% of those who use drugs as users and 99% of non-users as non-users. Determine what's the false positive rate. Okay, so the first thing I'm going to do here is I'm going to go ahead and define a couple of symbols here. I'm going to let D represent those who use drugs at this company, the employees that use drugs. I'm going to say not D are those who are non-drug users, employees that don't use drugs. I'm also going to say that the plus sign represents positive results and the negative sign represents negative results. When we try to determine the false positive rate, we're trying to figure out how many people actually test positive that actually do not do drugs. Okay? So in order for us to do that, I'm going to go ahead and create a tree diagram. When I create my tree diagram, I start with a node, which is just a starting point. So you always have a start point. So starting from there, there's two possibilities. Either I could choose a person who does drugs, and I'm going to go ahead and mark that as a D, or I could choose an employee that doesn't do drugs, and I'm going to mark that with a not D or a tilde D. The probability that someone does drugs at this company chosen at random is going to be 0.05, and the probability that they don't do drugs just by chance and random assignment is going to be 0.95. The probability that they're going to test positive from this group of people, so I'm going to say positive here, is going to be 0.99 because these people do drugs, and our test is 99% correct, so it's going to 99% of these 5 people are going to test positive. But then there's going to be 1% that actually tests negative. If I go from the non-drug users, what I want to do is I want to find how many people will test positive that don't do drugs and how many people will test negative that don't do drugs. If they don't do drugs, 99% of them will test negative. But there is the unfortunate 1% of those who don't do drugs that are going to test positive, and there's 1% of them. So this question says, determine the false positive rate. So a false positive means that this is going to be a person that does not do drugs and at the same time they test positive on the test. So what we're looking for here is what's the probability that someone does not do drugs and they test positive. And so there's only one way that we could get there, and the only way we could get there is to go down this route to the non-drug user and then go down this route to test positive. So if we do that, we have to multiply our 0.95 times the probability that they're going to test positive, which is 0.01. And we're going to get that this is approximately 0.0095. This is going to happen approximately 1% of the time. Okay, so this is going to be a 0.95% chance. So there's a 1% chance that we're going to choose somebody that doesn't do drugs, but they're going to test positive. Now, depending on the size of your company, 1% might not be that big of a deal, but if you have a large company, that could be a big deal. For example, if you work at a company where there's 100,000 employees, which is a very large company, but 1% of them are false positives, right? And you have 100,000 employees, that means there's 1,000 employees that are going to test positive for this drug, or for drugs in general, when in fact they actually don't do any drugs. And so this is how we would calculate this. And so we're going to look at this kind of idea over the next couple of questions, and let's see if you can answer some questions here. So now that we found the probability of a false positive is approximately 0.0095, let's see if we could find the probability of a false negative. See if you could use the tree diagram and calculate what's the probability of a false negative. So the probability of a false negative is going to be 0.05 times 0.01, or 0.0005, which is really small. So the probability that we're going to get someone who's a false negative is really small. But there is a 1% chance that we're going to, approximately a 1% chance that we're going to get a false positive. What are the consequences of each? What would happen if you don't do drugs and you are suspected that you do drugs? You take a test and they say, you know what, it came up positive. What are the consequences of a false negative? Some coworker, you work with a coworker, they do drugs, but they test negative. What are the consequences of that? Which area is worse? Now, of course, this is all completely opinion-based, so just in your mind, which one would you think is worse? Is it worse for the employee or worse for the company? So is a false negative worse for the employee or worse for the company? How about a false negative? What if this was an AIDS test? So now let's talk about AIDS. What's worse in an AIDS test? A false positive or a false negative? So if someone actually has AIDS and they test and their test says negative, is that worse? Or is it worse to tell somebody, oh, you have AIDS, but in actuality they don't? And so these are actual things that can occur, and so we want to always kind of consider what are the probabilities of each event. That being said, see if you can calculate this. If a person tests positive, given that their test says positive, what's the probability that they actually use drugs? Pause the video now and see if you can answer this question. So what this question is really asking is, what's the probability that someone does drugs given that they tested positive? Okay, so what's the probability that someone actually does drugs given that they tested positive? And so remember, whatever we're given, and we're given that they tested positive, that becomes our new total. So the first thing we have to do is calculate what's the probability of a positive. So we have to do the probability of that they do drugs and they test positive, and what's the probability that they don't do drugs and they test positive. So we've already calculated the probability that they don't do drugs and test positive. That's called a false positive. We have to find the probability that they do drugs and test positive, which is called a true positive. So the probability that they do drugs is 0.05 if we randomly pick somebody, times the probability that they test positive, which is 0.99, which is going to equal 0.0495. So the probability that they test positive is the probability that they don't do drugs and test positive, or that they do drugs and test positive, which means we add those two probabilities together, which is going to give us 0.059. So that's going to become our new denominator in order for us to answer this question. So that means that our denominator is going to be 0.059. Now, what's the probability that they actually do drugs, given that they tested positive? So remember, from this new group, we want those who tested positive and do drugs. Okay, so from this group, what's the probability that they do drugs and tested positive, which is 0.0495. So if we calculate that, that's going to be approximately 0.839. So in other words, or 83.9% approximately. Okay? In other words, if they tested positive, these are the people who tested positive, and this, remember, this test is 99% accurate. Okay, so it's 99% accurate or 99% effective. Sometimes they'll say effective. Okay, and so a lot of people think that if it's 99% accurate or 99% effective, that means that 99% of the time it's going to give us the right answer. That means if they tested positive, we're 99% sure that they're going to actually be positive, but not in actuality. In actuality, there's only an 83% chance that they actually do drugs if they tested positive. And so we have to be very careful, because when it comes to conditional probabilities, it's not always what you think it is. And so our intuition kind of fails sometimes when it comes to conditional probabilities. And the only way of doing that is mathematically. That's the only way to be absolutely sure what the probabilities are, is to do it mathematically. And so the probability that someone actually does drugs if they test positive is actually only 83%, using a 99% accurate or effective test. So that test that's supposed to be 99% effective isn't really what you think it means, right? When we say that the test is 99% accurate or 99% effective, that's not exactly how a lot of people interpret that. Okay, so in any case, the probability of that was 83.9%. It's much easier to think about independent events than to deal with conditional probabilities. It seems that most people's natural intuition for probability breaks down when it comes to conditional probabilities. So don't fall into this trap. When we see probabilities multiply, always ask yourself, are they independent? If they're not independent, then the probabilities may not be what you think they are. Okay, so let's go ahead and look at another example. Emily is going to get married tomorrow in an outdoor ceremony in Palm Springs. In recent years, it's rained only 5 days each year. So it's only rained 5 days a year in Palm Springs on average. Unfortunately, the weatherman has predicted rain for tomorrow. When it comes to rain, the weatherman correctly forecasts to rain 70% of the time. When it doesn't rain, he incorrectly forecasts to rain 9% of the time. What's the probability it's going to rain on the day of Emily's wedding? So see if you could create a tree diagram and answer this question, and then come back to me once you have an answer. Okay, so in order to answer this question, I'm going to first set up some variables to represent certain events. I'm going to let R represent the event of rain, and I'm going to let N represent no rain. I'm going to let F represent that the weatherman forecasts rains, and I'm going to let D represent that he doesn't forecast rain. And then we could, of course, use something else, but I'm just going to use this for now. Now, in order for me to create my tree diagram, I'm going to start with the start node, so that's just a little dot, and that's just going to be my starting point. From here, we could either have rain or no rain. So either it's going to really rain or it's not going to rain. And According to our data, it says that 5 days a year it's going to rain. So the probability of rain on some randomly given day is going to be 5 out of 365. And the probability that it's not going to rain in Palm Springs is 360 out of 365. So don't forget that out of each node, if you add up your probabilities, it should always add up to 1. From here, either the weatherman either forecasts that it's going to rain or he forecasts that it's not going to rain. Those are the only two possible possibilities. Either he thinks it's going to rain or he doesn't think it's going to rain. Okay, so if it rains, it says that he actually forecasts correctly 70% of the time. So this is going to be 70% of the time. When it rains, he says it's not going to rain 30% of the time. When it doesn't rain, it says that he incorrectly forecasts rain 9% of the time. So he's going to forecast rain 9% of the time, even though most of the times it doesn't. And then that means that 91% of the time, he's going to say it doesn't rain. It's not going to rain, and it actually doesn't rain. Okay, so here it says, what's the probability it's going to rain on the day of Emily's wedding, given the fact that the weatherman has already predicted rain for tomorrow? So really what we're trying to calculate here is what's the probability of rain given that he forecasted rain. Okay, so what's the probability that it rains given that he forecasted rain? So that means that our new denominator, is that he's going to forecast rain. So anytime that any end game where he forecasts rain, we have to add those together, and that's going to be our new total. And then anytime he didn't forecast rain, then that means that that's not actually part of our study anymore. So that means that this right here where he didn't forecast rain, we don't really care about that. We only care about the places where he forecasted rain. So let's go ahead and calculate this first one. What's the probability that it's going to rain and he's going to forecast rain? So the probability of that is going to be 5 over 365 times 0.7, or in other words, this is going to be 0.00958, I guess, or 59 if we go a few more decimal places. What's the probability he's going to forecast rain when it actually doesn't rain? Well, that's going to be 360 divided by 365 times 0.09. That's going to give us 0.08876, or 77 if we go a few decimal places. So if we add those together, we're going to get approximately 0.09836. And I'm just going a few more decimal places because I know my answer. I want to go 3 decimal places, so I go a few more just in case. Now, from here, we want to see what's the probability it's going to rain. So out of these two, because those are the only two we're interested in now, because that's our new population, that's our new total, out of those two, where do we see rain? And we see rain in this first one right here. This represents that he forecasted rain, and it actually did rain. So that means that our numerator here is going to be 0.00959. So let's go ahead and calculate that. What is the probability it's going to rain if the weatherman forecasted that it was going to rain? So it's going to be 0.00959 divided by 0.09836 approximately. And what we get here is the probability of rain, given that he forecasted rain, that's going to be approximately 0.097. And so there's a 9.7, or a 9.7% chance of it actually raining when the weatherman forecasts rain. So if Emily is getting married in Palm Springs and the weatherman forecasts rain, I would say, you know what, go for it. The chances that it's going to rain is still pretty small. It's only about 10%. Okay, so let's go ahead and look at a few more questions here, and let's see how you guys do on it. So Science Magazine reported that a computer using clinical proteometrics could examine blood samples and detect certain patterns relating to ovarian cancer. So this is absolutely true. Ovarian cancer afflicts approximately 1 out of every 5,000 women. The test can correctly detect the presence of ovarian cancer in 99.9% of women. So that means that if a person really, or a woman actually has ovarian cancer, this computer program can look at your blood, and 99.97% of the time, it's going to say you have ovarian cancer if you actually have ovarian cancer. Unfortunately, it gives a positive result when a person doesn't have cancer 5% of the time. If a doctor were handed a list of 1,000 patients who tested positive for the test, approximately how many would actually have ovarian cancer? So see if you could pause the video now and answer this question. Okay, so for the sake of simplicity, I've already created my tree diagram here. The probability that someone has cancer is 1 out of 5,000. The probability that someone does not have cancer, so not C, is going to be 4,999 over 5,000. If they have cancer, we know that the test is 99.97% effective in stating that they actually have cancer. And then that means that there's a 0.0003 chance that someone has cancer and it doesn't detect it. Now, of those who don't have cancer, 5% of the time it's going to say they have cancer, and 95% of the time it's going to say they don't. And so what this question is really asking is, what's the probability, right, that they have cancer if they tested positive? So what's the probability that they have cancer if they tested positive? And in order to do that, what we have to do is we have to first figure out where all of our positive cases are. And so our positive cases happen to be here. So this is a positive case right here. And then this is also a positive case right here. So that's our new population. Everything else we don't need. We're just going to cross that out. So these are the only two that we need, and we're going to go ahead and add those together. So if you were to add those together, you would basically get 0.05019 approximately. Now this is approximately. So let me actually say approximately here. And then what we want are those who actually have cancer. So those who actually have cancer is this right here. So that's going to be 0.0002. So if you test positive for this cancer, what's the probability that you're going to actually have cancer? So we're going to take that 0.0002 and divide it by 0.05019. And what we get is that is approximately 0.00398, okay? So listen to what this is saying. Out of 1,000 positive, right, out of 1,000 positive test results, our probability shows approximately 3.98, or we're going to, of course, these are people, we're going to say approximately 4 people actually have the cancer, okay? So think about that. This test is 99.97%, and what they'll say is 99.97% effective, okay? It's going, if you have the cancer, 99.97% of the time, it's going to say you have the cancer. But of the 1,000 people who tested positive, actually only 4 people have this cancer. Okay, so we have to be very careful about positive results. And if you're wondering, what in the world? How is this possible? How is that true? And this is an issue of something called prevalence. And prevalence is what proportion of the population actually has it, and is it very, very, very small? Okay, so think about this. So this cancer affects 1 in every 5,000 women. So that means that if you look at 50,000 women, so we're just multiply it times 10. So if you look at 50,000 women, that means that 10 of those 50,000 women will actually have cancer, approximately, right? So approximately will have this cancer. So that means that if you to test those 10 women that have this cancer with 99.97% effectiveness, those 10 women pretty much will test positive, right? But the problem is there's a 5% false positive case, which means that 5% of the other remaining 49,990 women who test to get this cancer, 5% of them are going to test positive, but they're not going to have this cancer. And that number is so massive compared to the 10 that our probabilities just don't match up. And so this is one of those real defining cases. This is an example of one of those cases where if you don't understand conditional probabilities, right? If you don't understand it, then your intuition of what probability means of 99.97% effective, that is not as effective as you think it is. And so what we see is 0.4% of those who actually test positive actually have this cancer based on these results. And so you might say, well, what does that mean? What that means is they'll probably do some kind of more, for those women, those 1,000 women who did test positive, they're going to probably do something more intrusive, a test that's a little bit more, more than just looking at their blood. They're going to actually do some kind of MRI or something like that, or maybe even some kind of incision and do some kind of microscopic exploration or something like that, where they could be sure whether or not they actually have the cancer. But we have to be careful. When you take a test and they say it's 99.97% effective or accurate, that 99.97% is not what you might think it is. And so when we say here, of those who actually tested positive, if they tested positive, what's the probability that they actually have the cancer? Well, 4 out of 1,000. And that's not very high. Okay? So that's a pretty interesting example of where probabilities are not exactly what we think they are. Okay, so that being said, here's another example that I would like for you guys to do, and I'll just give you the answer to this, and then I think that this video has gone on too long already, so I'm going to end this kind of short, and I'm going to have you go to Desmos, answer these questions, and then I have a few more questions for you guys to answer on your own. So go ahead and pause the video and see if you could answer this question about psoriasis. Okay, so if you answered this correctly, what we're looking for is what's the probability that a person tests positive, and that's going to be the probability that they test positive given that they have psoriasis and that they test positive given that they don't have psoriasis. And so the probability that they have that they test positive and have psoriasis is 0.01994, and the probability that they test positive given that they don't have psoriasis is 0.049. And so the probability that someone's going to just test positive is 0.06894. What's the probability that a person selected at random who tests positive for this disease doesn't actually have the disease? So once again, what's the probability of a false positive? Go ahead and pause the video here and see if you can get the answer. Okay, so if you did this correctly, the probability that someone doesn't have psoriasis given that they tested positive, in other words, it's a false positive, once again, it's going to be 0.049 over 0.06894, or 71%. And so here, in this case, once again, in this particular case, the probability of it is going to be 71%, which is something that you might not have expected. All right. So suppose a die has 4 9s and 2 zeros on its faces. So it's a weird die. It has 4 9s, sorry, and then 2 zeros. Die B has 4 3s and 2 11s on each face. Each face of both dice have an equal chance of landing up on top. So basically both dice are fair, although we have different possibilities for each die. 2 players play this game. The first player selects a die and then rolls. The second player must roll the remaining die. So there's 2 die. The first player decides they get to pick and choose which die they're going to roll. They roll it, and then they're going to get a number. The second player is going to choose the remaining die, and they're going to roll their die. Whoever has the highest score wins. That being said, if you're the first player, which die should you choose and why? See if you can calculate this probability and then answer this question. Okay, so in order to answer this question, what I would do is I would first create a table. So in this case, I would go ahead and see what happens with die A versus die B. And in die A, we could get 9999 or 00. On die B, you could get 3333 or 1111. Now, if die A is a 9 and die B is a 3, die A wins. And then you can see on this table, I placed A's where anytime A would win, and I put B's anytime B would win. And if you count all your A's and B's, and there's 36 possibilities here, you can figure out the probability of each. So the probability that die A is going to win is 16 out of 36, or 4 and 9. The probability that die B will win is 20 out of 36, or 5 and 9. So if I were going to play this game, I would choose die B because it has a higher chance of winning. Now, does that mean that you will always win? Absolutely not. Does that mean you will win the majority of the time? Not necessarily. What this tells me is if I play in the long run, if I play many times, I'm going to win more often choosing die B than by choosing die A. Okay, so there's a lot of information about COVID-19 circulating amongst the populace. So with this much information or misinformation that's getting passed around, sometimes it's difficult to actually understand or to know what's fact and what's opinion. And so what we're going to do is we're going to let probability tell us what is fact and what's opinion. We're going to let it be our guide. And so what I would like for you guys to do is finish the rest of this lesson in Canvas, answer these questions, and if you answer these last questions, I'm not going to say that there's a right or wrong answer. I'm just going to try to let you answer it on your own and make up your own decision. But if you make up your own decision, answer these questions, I'll give you a little bit of extra credit. All right, guys, thanks for watching the video. Bye for now.